Okay, so objective 2, what we're doing is classifying a linear system of equations as either consistent or inconsistent. So take a look at this rather dramatic picture. Okay, so in the picture it kind of details the three cases that we're talking about. So one case is maybe these lines intersect each other, like these railroad tracks intersect each other at this point right here. Okay, so that's one case. Another case is, well, what if the lines are parallel to each other, like the lines on each side of the railroad tracks? They never intersect each other, there's no solution. And then finally, the other one was, what if they intersect everywhere? So where these two lines intersect right here, after they intersect, they become the same track line, and so there's infinitely many solutions right there. Okay, so that's what we're talking about here, and they have special terms, consistent and inconsistent. Okay, so when we solve a system of equations, there's three possible outcomes. The first one is you have exactly one solution, one point of intersection. You graph the two lines that intersect at just one point. In that case, it is a consistent system. The word consistent means you can find an answer, okay? And then the independent part of it means that the answer does not depend on either one of the equations. It is one and only one solution. So whenever I have one solution, one point intersection, I'm going to say that it is an independent, consistent system. Okay? One solution is independent and consistent. The next possibility is if they intersect everywhere, they have infinitely many solutions. So since it has at least one solution, we're still going to call it a consistent system. But the solution depends on one of the equations. So we call it a dependent consistent system. So if we go to graph our two equations and they end up being the same line, I'm going to classify it as dependent and consistent. Okay? Again, consistent means I have at least one answer, at least one solution. The dependent means that I have multiple answers. I have infinitely many answers. Okay? And then the final case is if these things, whoa, wiggle. The final case is they have no solution because the graphs themselves are parallel to each other. So they have no point intersection, and this means I'm not going to find an answer. It is an inconsistent system. Inconsistent means that whenever I try to solve it, I don't get an answer. An inconsistent system. Okay? I think this one will wiggle too. Oh, there you go. So let's go back to those previous exercises. It's going to be a very short video here. Go back to those previous exercises right here. I have them graphed, and in number one, whenever I graph the system and I solve it, I have one point of intersection. If I have one point of intersection, this means that it is an independent what happened to my letters? Independent consistent system. So consistent means that they have an answer, at least one, and independent is just one of those answers. Okay? Same thing is true about this number 2 here, so I'm just going to circle this and bring it right over here too. That since it has a solution, it is consistent, and since there's only one of them, it is independent. Okay? On these two, on number 1 over here on the left hand side, whenever I graphed it, it was the same line. If it's the same line, it has lots and lots of solutions, infinitely many solutions, so it is at least consistent. But each one of those solutions depends on just one of the equations. So I'm going to write dependent consistent system. Okay? And on number 2, I go to graph them. They are parallel. They have no points in common. This is an inconsistent system. There's no solution. So this is inconsistent. All right? And that's pretty much it in terms of the vocabulary. So I'm going to kind of lead into the next lesson by talking about this final exercise, a word problem. Let's read it together, shall we? A soccer league offers two options for membership planes. Membership planes. I think that's supposed to be plans. Okay. Anyway, option A includes an initial fee of $40 and costs $5 for each game played. Option B costs $10 for each game played. Just no startup fee, just $10 per each game. After how many games will the total cost of the two options be the same? So I have two options. I have an equation for each, and if I solve this as a system of equations, I find the number of games in which the amount of money that I had to pay is exactly the same. Okay, so let's define our variables. X is going to be how many games that we're playing, so that's X. And Y is just going to be the amount of money that I pay out total. So an option A, I'll just write this up at the top. Option A, the amount of money that I'm going to pay, well, each game is $5 each. So $5 times each game played, so 5x. But I have a startup fee of $40, so I'm going to add 40. So even if I don't play any games, I still have to pay 40 bucks. Okay. Option B. Option B, there's no startup fee, it's just that each game is 10 bucks. So 10 times x. So you can see that option B is a little bit cheaper, or at least it is at first, because if you play one game in option B, it's just $10. If you play one game in option A, you already have to pay 40 plus an extra $5 for that game. That's 45 bucks. So our question is how many games do you have to play so that these plans balance each other out? So what we were doing in this previous lesson is we were just graphing each one of these and see where they intersect. Okay. But whenever you have a y-intercept like this at 40, man, that's kind of a headache to have to graph. So another way to solve this system of equations is maybe I just do it by substitution. They're both equal to y, right? They're both equal to y. So remember from geometry, the substitution property is if they're both equal to the same number, I can take that number out and replace it with something that's equal to in its place. So I can take out this y and I can put in 10x in its place because they are equal to each other. All right, 10x is equal to 5x plus 40. Okay, and then solve this as just one single equation. Subtract over the 5x and I'd have another 5x equals 40. Divide by 5 and I get 8 games. Right? So let's just stick that in here. If I stick it into the bottom one, I get 10 times 8 would be equal to $80. So our point of intersection, if we graph this, would be 8, 40. So, no, that is not right. 8, 40. Silly. 8, 80. So after 8 games means that these two things cost the same amount. And after that, option A becomes a better deal and option B becomes a worse deal. So there we go, 8 games.